Welcome. In this video, we will be using CNN models to predict tropical systems from satellite images. Tropical systems such as tropical depressions, tropical storms, and hurricanes have become more prevalent and stronger over the past few decades. These storms rank as the costliest weather disasters among other weather phenomena such as floods or droughts. And despite better forecasting over the past decades, unfortunately more lives are being lost to these storms. So we want to see if CNN models can help meteorologists predict weather disasters, and more poignantly for this project, tropical systems. The software used for this project is readily available and can be downloaded from the internet. We are using standard Python libraries and TensorFlow. TensorFlow allows us to run these models on GPU in a parallel environment that is more efficient than running on a single CPU. It also has the ability to read and process images and to label them if we set up the proper directory structure. This project runs on Windows 11, but it's not dependent on an operating system, and we are using a GPU for this. To download the data, we are using web.org. This is a website that archives other websites and captures their information. We want to use this because nhc.noaa.gov does not archive their images. If we were to go to the website now, it's just going to have the current radar, but not a radar going back for 8-10 years as we are doing for this project. So for the range, we're setting July of 2014 to November 2023. We are using an API to get JSON from web.org that tells us if it has those web pages available. If it has those web pages, we will navigate to those web pages to download the image and accompanying forecast text. The forecast text or forecast discussion is important because this is going to help us label the images. If there is calm weather, there are certain literals that we can find in the forecast discussion. This is going to help us label that there is no active storms, or 0. If we do not find these literals, we are going to label the image as 1, meaning that there is an active storm. An active storm could mean a hurricane, tropical storm, or a depression. We want the model to identify if there is a tropical system there or if the weather is calm. We have found 252 total images for the Atlantic Basin, and we found 274 images for the Eastern Pacific. To set up the directory for the CNN models, it's going to follow a standard train, validation, and test directory. We are going to have 2 directories under each folder named CALM and STORM. The reason we're doing this is because the image data generator under TensorFlow has the ability to assign labels just based on the folder structure, which is very convenient when feeding the images into the CNN model. We're going to be using 60% of the images for training, 30 for the validation, which will evaluate how well our CNN model is doing, and we're going to set aside 10% of the images for prediction. These are images in the test directory that are not seen during testing or validation for the best possible prediction. The CNN model we are using is going to have 3 convolution layers, each having a max pooling. By the convolution layers and the max pooling, we're going to be able to find the hierarchical features from the input images we're feeding into the model. We'll see that the total training parameters are increasing from layer to layer because we are increasing the nodes from layer to layer. All told, we have 42 million trainable parameters, which are 42 million nodes within the CNN model. Eventually, we will flatten the layers so that we have a binary classification of 0 or 1, and in this case 0 will be storm, 0 will be calm, and 1 will be storm. And again, this goes back to the directory structure that we set up from the image generator. When we fit the model, we saw that immediately it had high training and validation accuracy, and the loss was also very low, which is a good sign. Around 7 epochs, we saw that it started to overfit, which is a sign that we didn't really need a lot of epochs in there. The number of steps was actually the length of the images that we're feeding into the model. And this was really because we didn't have enough images. So we could see that it started to overfit, probably because we didn't have enough images to feed into the model. Nonetheless, we went and predicted the model, and it was 100% accurate. So the predictions really reflected how well the model's trained and the validation accuracy within the training. The confidence threshold was a percentage that the prediction returns. And the lower the percentage, the more it's to label 0, and the higher it's more to label 1, which is a storm. So we had the threshold set at 0.5. Anything below 0.5 was calm, and anything above that would be labeled as a storm. But we want to be sure exactly where this model is looking, since it is so accurate. The first thing we did was we took the Laplacian edge detection. By using filters and striding across the image in an array form, we're able to highlight specific values and really have them stand out in the image. And as the arrows indicate, we see that the model is really focusing on the symbols and the text rather than the cloud patterns, which is what we want the model to train on. So we are able to see that the model is looking and seeing differences between calm and storm, but it's not really looking at the place that we want it to. Another way we're able to determine how this model is determining what is calm or storm, or how it assigns the label, is by looking at the convolutions. So here we have the layers 1, 2, and 3 and the original image, and we can see the progression of what these models are really focusing on and what the layers are really focusing on, because each layer has more and more nodes on there, and the weightings seem to be focusing more on the symbols and the text rather than the cloud patterns that we want it to see. So we'll see the convolution layers from the input down to the last layer before flattening and assigning the label, and we see the text and the symbols very prominent in all of these labels. So to combat this, we thought that maybe we could augment the images before feeding into the models. Again, since we had a limited amount of images that we could feed into the model, we want to somehow duplicate or make more images, but not make them the same, because the model is just going to give us the same output. So the only trick with being able to augment an image is we have to maintain some type of structure with the cloud patterns that we're feeding into the model. The storms have a very specific signature, especially hurricanes. You see the eye, you see the swirling bands outside of the storm. However, if we were to flip this horizontally or vertically, that would not be the signature storm that we are looking for in the northern hemisphere, which is the northern Atlantic Basin and the eastern Pacific Ocean. So we decided to use 3 other augmentations. We rotated the image, and we increased the width, which kind of stretches out the image, and then we shifted it up. By doing this, we didn't want the model to train on specific regions or outlines of the land, and by zooming in or rotating it, it kind of replicates what a tropical system would look like. Tropical systems are all different sizes, but as they increase with intensity, they start sharing the same shape. So we took all of those images, now augmented, which increased the training images about 5-fold, and we saw that the training was increasing. It hit a high number, but didn't seem to be overfitting as quickly as the smaller images. But the validation accuracy was straight on. It did not change from epoch to epoch, and we see that reflected in the loss as well. Very low loss, and the training started to maybe around 7 or 8. We see some signs of overfitting with the validation loss that's up there. So we didn't need a lot of epochs, but it didn't seem that the augmentation has helped out at all. Again, it was 100% accurate, and the confidence was even higher. I mean, these were full 1s and 0s for detecting a storm and or calm weather. So the augmentation really didn't seem to help. It really seems like finding more images and passing them into the model would be the right approach. So I think that is the biggest hurdle to overcome for this project. We did see that the models could properly predict a storm or calm weather. It just was looking at the text and the symbols. If we were able to find images that could be labeled based on the forecast discussion, but without the text and without the symbols in there, I think we could have a pretty accurate model that comes out of this. The other thing is, it's for doing this type of work, processing images, it's really recommended to use a GPU. With 42 million nodes and with lots of images being fed into the system, it can parallelize well on the right configuration. And the first model took about 3 minutes to run, and the augmented images took about 25 minutes to run. So if we have a model with thousands of images, it's going to take hours to run, even on a powerful GPU. But there is hope. Even though we hit a stumbling block with the networks focusing on text and symbols within the images, with satellite images and with the CNN being able to detect signatures within the clouds, I think this model could help meteorologists predict storms on the horizon and could be a very successful aid in their prediction as we incorporate more and more images into the CNN models. Thank you for watching.